Okay guys, so today what we're going to look at is intersection and unions. But first, in order to understand that, we have to understand a basic concept in sets, which is Venn diagrams. So this is your first Venn diagram, and a Venn diagram basically shows relationships between different sets. So in this case, we have a Venn diagram that shows a relationship of people who like ice cream and people who don't like ice cream. Specifically, grade 10 teachers. So as you can see, teachers that like ice cream, Mr. David, myself, Mr. Majid, Mr. Abel, Mr. Stanley, and Mr. Matt. So these are people who like ice cream and are part of the set A of people who like ice cream. Over here we have A complement, which is basically not A. Okay, we can call A complement as the same as not A. And that basically means people who don't like ice cream, right? People who are outside of this set. So in this case, I put Mr. Sharif there and Miss Charlie. Now, I don't really know if these people like ice cream or not. I just sort of made it up for this example. But there we go. So the first property of Venn diagrams is that if we define E, or epsilon, as the universal set, okay, and in this case the universal set is all grade 10 teachers, okay, if we define that as universal set, the number of A plus the number of A complement must be equal to the total number of population within the universal set. So in this case, the number of A is 1, 2, 3, 4, 5. The number of A complement is 1, 2. And the number of people within this whole box, within this whole Venn diagram, is 7. So that is our first property of Venn diagrams. Okay, so now let's take a look at the idea of intersection. So the definition of intersection is this little upside down U, right? And if we have the definition, let's try this again. Okay, so now let's take a look at the idea of intersection. And the definition of intersection is E intersects H, where all of X's, and X is a member of E, and X is a member of H. So we would basically say E intersect H. And basically it's just an and, right? The key word here is and. We're looking for members of both sets that intersect, right? That's what intersection means. In this case, if I give an example, E is the set of teachers who like ice cream. Okay, let's say that's the same as last example. So Mr. Majid, myself, Mr. Abel, Mr. Stanley, and Mr. Matt. And H is a set of teachers who like pizza. Mr. David, Mr. Stanley, Mr. Abel, and Mr. Richard. We can create this in a Venn diagram. And the place where both circles overlap is the intersection point. So let's look at which teachers overlap. Well, we have myself, I like ice cream and pizza. Well, Mr. Stanley apparently likes ice cream and pizza. And also Mr. Abel seems to like ice cream and pizza. So we can put them in this intersection point right here. We've got Mr. David, we've got Mr. Abel, we've got Mr. Stanley. Now outside of this intersection point would be teachers that, for example, only like ice cream, or teachers that only like pizza. So which teachers only like pizza? Well, according to this, Mr. Richard only likes pizza, but he does not like ice cream. And according to set E, it looks like Mr. Majid and Mr. Matt only like ice cream, but don't like pizza. And keeping in mind, we can also still include teachers who don't like any of these, right? There are some teachers who don't like ice cream or pizza. For example, maybe Miss Charlie. Right? So maybe Miss Charlie doesn't like ice cream or pizza. We would write her outside of the Venn diagram. But still part of the universal set, which is grade 10 teachers. Okay, so continuing our examples, now we're going to take a look at the idea of union. So this looks a lot like intersection, the thing that we just looked at, but this is a little bit different. Instead of the upside down U, this is a right side up U, right? So this we call E union H. And the key for union is that instead of x is a member of E and x is a member of H, we just say x is a member of E or x is a member of H. So as long as they are a member of one set or the other, or both, they are considered part of this set called E union H. So in this case, the teachers who like either ice cream or pizza would be basically all the teachers inside the circle, right? So Mr. Majid, Mr. Matt, Mr. David, Mr. Abel, Mr. Stanley, and Mr. Richard. They're all part of the set E union H. Now, does it matter that Mr. David, Mr. Abel, Mr. Stanley like both pizza and ice cream? No, it doesn't matter, right? Because they're still considered part of the set that includes the or. Does it matter that they're in both sets, so should we list them twice? No, not really, right? We still only list, Mr. David, Mr. Abel, Mr. Stanley only one time. We don't put them twice in this set. As long as they are part of one of these sets or part of both of these sets, they are considered part of E union H. Now, as a quick check, if I said E union H complement, right? Not E union H. What would that be? Take a minute and pause and think about it. Okay, so in the example E union H complement, as in not E union H, well, that basically says everything that's not inside of E or H. So in this case, all we have outside of the bubbles are this Charlie, right? So this set E union H complement would be this Charlie. Okay, guys, so now let's take a look at a couple of more properties that relate to sets. In this case, we want to talk about the idea of disjoint. And the definition of the disjoint is when we have two sets, A and B, that when they intersect, they form the null set. And remember, the null set, the symbol null set, just means that there's nothing inside that set. So this is an example of a disjoint situation. If we have a set of A which has the numbers 1, 2, and 5, and the set of B which has the numbers 3, 6, 8, and 9, there's no overlap between A and B, right? There's no number that is in both set A and in set B. So we would call these two sets disjoint. Okay. Now, also in general, and this is a general property that applies to all sets, not just this example, A union A complement is going to equal the universal set. And if you think about that, that basically makes sense, right? Everything inside A plus everything that's not inside A, right, all this stuff outside, should equal all the stuff within this universal set. Right? So A union not A should equal the universal set. And by the flip side, A intersection not A should be equal to null set, right? If I say everything inside of A and compare that with everything outside of A, is there any intersection? Well, no, right? Because by definition, everything outside of A is outside of A. That's what A complement means. And by definition, everything inside of A is only inside of A. So how could we possibly have an intersection between A and A complement? So by definition, it must be the null set. There's nothing that intersects between the two sets. Okay, guys, let's take a look at example number 17, which is on page 14 of your book. And in that example, we have a universal set, which is the letters P all the way to W. And we have set A, which is PQRS. We have set B, RST. And we have set C, which is STUVW. And the question asks us to find the number of elements within A union B, and also to list the elements of A union B complement and A union B union C. So let's take a look at it first by drawing a Venn diagram. And when I draw a Venn diagram, what I want to do is I basically go through all the elements and I see which sets they are a part of. So in this case, element by element, let's start with P. Well, P looks like it's only a part of A, so let's put P in A. Let's look at Q. Q is part of A and nothing else. We've got R, and R is part of A. It's part of B also. So it should be right here. Okay, what about S? S we have in A, we have in B, and we have in C, so S should be in the middle, shared by all three sets. Okay, T is part of B and part of C, so we'll put T over here. U, what about U? U is part of only C. V is part of only C as well. And W is also part of only C. So, in this example, first thing we want to find is the number of elements within A union B. Remember, N bracket means the number, right? Not what is in A union B, but the number of elements within it. So, what is in A or B? We have P, Q, R, S, T. That is 1, 2, 3, 4, 5 elements. So this should be 5. The answer is 5. If we asked you for the elements of A union B, if the question was just this, A union B, then you would have to actually list out P, Q, R, S, T. But in this case, it's asking for the number of elements. Okay, secondly, we're asking us to list the elements, and this is where we actually have to write out what is there. So A union B complement, A union B complement. So that means A union B is these two guys and everything that's outside of it. So what is outside of A or B? Well, that's these three guys over here, right? W, U, and V. So A union B complement is U, V, W. Right? And what about A union B union C? Well, that's either A or B or C, so it's everything that's inside these three bubbles. In that case, every single letter, right? The entire universal set. We can basically write it as that. Okay, guys, I know you're tired, but this is the last example, and this is example 7 from your book. If you take a look at the problem, it says that the universal set is basically X, where X is all the numbers between 2 and 30, and X is a member of the positive integers. That's what Z plus means. So X is a positive integer between 2 and 30. That basically means X is 2, 3, 4, 5, 6, 7, 8, 9, all the way to 30. Not 2.5, not 6.8, no decimals, right? Just full numbers between 2 and 30. And we have a set P. So we have a set P where it consists of X, and X is a factor of 30. So X is a factor of 30. And the question asks us to list the elements of P. Now, keeping in mind that X must be between 2 and 30. So if we begin, we must know that 1 cannot be part of P because 1 is less than 2. So the first member of P must be 2. Okay, what else is a factor of 30? Well, 3 is. And we have 5. We have 6. We would have 10. We should have 15. And we should have 30 itself. Because this is less than or equal to and less than or equal to. So we're including 30 and 2. The second part asks us to describe the set P complement. So P complement is basically everything outside of P, but still part of the universal set. Right? Everything that's part of the universal set outside of P, and we would write it like this. So X, where X is not a factor of 30. So that would include numbers such as 4, right? There's no 4. 7, 8, 9, those are not factors of 30. All right, finally, we want to find the number of P complement. So what are the number of elements within this set P complement, right? That's what this N again means. So we could find that by subtracting the number of universal sets and the number of P set. Right? So N P complement should equal the number of elements within the universal set minus the number of elements within P. Right? That's one of our properties. So in this case, if we take the number of elements within the universal set, that's, if you count them, 2, 3, 4, 5, 6. If we count them up, you would find that the number of elements in there is actually 29. And you would find the number of elements within P, well, 1, 2, 3, 4, 5, 6, 7. So our answer, 29 minus 7, is 22. Okay? Thanks for all your hard work. I will not give you a practice problem because this was quite a long video. So I'll see you guys